Okay, so today we are going to be looking at linear relationships, and we looked at proportional relationships over the last few weeks, and we looked at linear and nonlinear relationships over the last couple days with our posters and our tiles. Today we're going to jump into a real world situation with the big race. So we're going to make that connection from just patterns in math into real world. And it's going to relate a lot of the stuff that you did in science, distance and rate and time. Do you guys remember doing that over the last week or two? Awesome. All right, so what we're going to do is I'm going to start you off with a simple question for the warm-up. A local donut shop sells baker's dozen of donuts for $12.98. Does anybody know what a baker's dozen is? Logan.
13.
Yeah, it's kind of awesome. You get an extra donut for free when you buy 12. So a baker's dozen of donuts for $12.98, and the grocery store sells 6 donuts for $5. If I was going to be the most awesome teacher ever and I was going to buy donuts for our class, we have 26 students in our class, which place should I buy them from? And I want you to justify your answer mathematically, and I want you to do this in your warm-up spot, okay? And there probably are some questions you might have, but I want you to think about those. I don't want to answer them just yet. Okay, so think about how you could justify which place I should get the donuts from and why. Okay, yes?
Wait, it is 26, right?
26 students are in our class. Yes. Okay, figuring out the answer is probably very easy, but justifying is going to be a little tricky. And like every warm-up, if you want to ask the person next to you, if you're kind of stuck on a question, you're more than welcome to. Okay. Are you done, Hagen? Can I see your answer? Let's see what you did. Hey, Jacob. I'm going to have you put yours under number 2 up on the board in just a minute, okay? Whoops, I'll put that up in a second. Yes?
So, are you trying to conserve money with this?
Yes, I want to be as cheap as possible.
The donuts might be grosser.
Sorry.
Wait, are you actually gonna really do this, or are you gonna like just, or are you just making a question out there? Or are you gonna actually?
Yes?
It doesn't talk about quality or which like a survey of which students like and all that.
I'll say I think Rayleigh's donuts are pretty good.
Okay.
And they're from a grocery store. Okay. I'm going to have you put your answer up at number 1. Okay? And yes. And yes.
The donuts in the grocery store come in like packs of 6, right? So you can get like one for a lower price.
Well, that's a question I'm going to let you think about. I didn't tell you for a reason. Okay? And then, Chloe, I want you to put your answer up under number 1. Okay, so everybody's had a few seconds. I've walked around and I've looked at a lot of people, and there's some really good ways to justify. If I told you to go up to the board and write your solution on the board, I have a section for 1, 2, and 3. I'd like you to come up and just write your answer on the board. Okay? And we're using black markers today. So if you're a 1, a 2, or a 3, come on up and write your answer on the board, and I've got markers right here for you. because they show up better. And Chloe, did I say you were the 1? Okay, you can be a 3 now. Okay, so yes. Okay, so they're writing their solutions up and they're justifying them. While they're doing that, let's talk about some questions you might have had from that warm-up question. What is a question you had, Logan?
For at the grocery store, if you could buy one donut at a cheaper price instead of having to buy a package of 6.
Okay, so do you think the donuts were what was it, 6 for $5?
Yeah.
So would you be able to buy one donut at that same rate? What do you guys think?
No.
Okay, Alan says no. Why do you think no?
Because when they say 6, they're gonna give you 6. And like you can't like take apart a box. Like you're gonna take apart a box and like take out 2 donuts from it and buy it. You can't do that.
Okay, so you can't take apart a box. But at the grocery store that I buy my donuts from, they have a big cabinet and I open it and I just pull them out.
Yeah.
Okay? So if they're boxed up, yeah, you can't really take out a box. Anybody think that you should be able to pay that same rate? Donovan, why?
Because like you said, whenever my family buys donuts, we always go to Raley's. And they have, like you pick and choose the donuts you want, and it's always a fixed rate for each donut.
Okay, so you get to pick and choose how many donuts you want. What about the donut shop where you get 13 donuts for $12.98? Do you think you can break those apart?
No.
Yeah.
Well,
Because some
Jessica?
I think that you could. Okay, so I think that at the bakery you could probably not buy a full baker's dozen.
Okay, so everybody has their solutions up. I'm gonna let Alex share his first.
All right, for the 6 for $5, it's 83 cents per one, and for the baker's dozen, it's $1 per one. And 83 cents is the very low because it's cheaper per one than the $1 the baker's dozen.
Okay, so what did Alex use to figure out his answer? Yes, Matthew. Sorry.
Unit rate.
A unit rate. So he found a unit rate. Unit rates are really important in proportions. Okay, Jacob, what did you do?
I thought the donut store includes a better price because 13 donuts for $12.98 is about $1, while 6 donuts for $5 is about $1.20.
Wait, do you mean $6 for 5 donuts?
6 donuts.
Yeah, 6 donuts for $5.
So wouldn't that be?
Isn't it 5 divided?
Yeah, it'd be like 5
Oh,
right?
I might have done it
Yeah.
switched up.
That's okay. So now we need to look at 6 divided by 5. What would that be?
6 divided by
120.
yeah, well,
About
Close to 83 cents.
I'll let you fix that.
divided by 2.
And Chloe, I'm going to have you share your answer.
Okay, so I got the cost per donut from both stores, and the grocery store's donuts are each around 83 cents. Are 83 cents per donut, and the donut shop's donuts are about $1 each.
goes in the box.
Are about $1 each, so therefore the grocery store's donuts are cheaper.
Okay, so what Chloe did was she also figured out what each donut cost. So all 3 of these guys figured out what each donut costs. But let's go back to what Alan said. Do you think we know for sure that you can pay you're going to pay $1 per donut for the dozen, or that you're going to pay 83 cents per donut at the grocery store? What do you think?
It was not Rayleigh's. Never says it's Rayleigh's.
Did anybody come up with a different answer? Because all of these said the grocery store was cheaper. Okay, William.
Well, my answer is the grocery store is cheaper, but then instead of getting the unit rate, I found how much it would cost to have 26 kids eat donuts and be very happy.
Okay.
So the local donut store, as I labeled it LDS, I used the proportion, so it was 13 to $12.98. And then so using the proportion, 26 donuts is X. So I got $25.96 for the local donut store. The grocery store, I did 3 proportions. Well, not proportions, but ratios. So $6 to $5 is 1 donut to 83 cents because 26 isn't divisible by 6. And so I multiplied that by 26 and I got $21.58. So the grocery store is cheaper to buy 26 donuts than the local donut.
Okay, and that's using that unit rate that all of these guys showed. So, Gabriel, I'm gonna let you answer. Do you have a question, or do you want to share your solution?
Well, I did get that the grocery store was cheaper, but it's not necessarily the better deal necessarily because it could be smaller donuts. The donuts could have been sitting out for a long period of time and gone stale.
Okay.
And terrible.
So,
There are several factors.
comparable quality of donuts, Gabriel.
That's very unspecific.
Okay.
It is high. It's a slightly higher likeliness that maybe the donut store has.
Okay, since they only do donuts, they're probably better. Did anybody think?
The donuts.
Okay. Did anybody think that the donut shop would be cheaper than the grocery store?
No.
Logan?
Well, because if I'm just assuming that the donuts come in boxes of 6,
Yes.
and you would have to get more, so it would be $30 to get them at the grocery store. Or no. Yes, yeah, $30. Because you'd have to get the overflow of donuts. You would have to get like 32 donuts or something, rather than just 26. And so it'd be more expensive.
Okay, so everybody that came up here found a unit rate, and I like that because unit
Yeah.
rates are really important in proportions. Logan, I agree with you
Yeah.
because I'm a pessimist. Sorry, I won't do that. I keep hitting the microphone. Sorry. So I'm a pessimist. I'm not necessarily a pessimist, but I'm thinking that if they say 6 donuts for $5, I have to get them in groups of 6. Otherwise, they're going to be $1.25 each. Or at the I might buy bagels a lot, not necessarily donuts, but you can get a discount when you buy 13 bagels versus a single bagel. So in my mind, I thought the donut shop would be cheaper because I could get the exact amount. I wouldn't have the overflow. Nobody would be fighting over this 4 extra donuts. Okay, and
It would most likely be better tasting.
okay, and according to Gabriel, they'll be most likely better tasting. Okay, you guys, thank you so much for coming up and sharing your solutions. We're going to move away from this warm-up that we spent an extra long time on today. And we're going to talk about where are we going. So we did tile patterns right here. Do you remember what was the same about all of these tile patterns versus these 3 over here? And I'm going to let you guys think for a second. Talk to the person across from you, and then I'll call on someone.
I know one reason, okay? Those 2 are exactly like the same pattern because they have the same amount of squares on each and they have the same formula. So
Okay, we're going to go a little quick through this section. So,
They have 2 binomials, so.
I heard this group right here talking about, what did you call these types of problems? Yes?
Quadratics.
Quadratics. What do you notice about quadratics?
4.
There's 4. What do you mean 4? Oh, quadratic, quad means 4. Okay, we'll make that connection later, but think about an x, and when we have an exponent of 2, what do we call that? X squared.
And
Huh. And a lot of these have squares in them. So those are quadratics. These are called non-linear because why would I call these non-linear? Someone give me one reason why I can call these non-linear. Haley.
Because if you were to trace it like with a line and a ruler, it wouldn't go all the way straight down.
Yeah,
It,
so
like,
right
curves.
here when we're looking at those graphs, it's not necessarily, this group didn't get to their graph quite. That was not a straight line. So what do we call these over here? Linear. And what are some things you can tell me about linear functions? Donovan.
They're not proportional because they don't go through the origin. But
Okay.
but if you were to trace them, they go in a straight line.
Okay, they go on a straight line. These are all not proportional because they don't go through the origin. Okay, are proportional relationships linear? Let me say this statement. Are all proportional relationships linear?
Yes.
Are all linear relationships proportional?
No.
No, okay. So what we're doing is we're taking proportional relationships and we're moving them to non-proportional relationships, but they're going to stay linear. Okay, so that's a big idea for today is we're going to be looking at a lot of different types of functions, and they're going to be linear, but they're not just going to be tile patterns, they're going to be real-world problems. So I'm going to put the board back up, and this will give us our goal for today and your challenge.
Are we gonna do this challenge in our group?
Yes. Okay, so looking around the room, did anybody see any proportional relationships?
No.
I kind of skipped this slide, got it a little backwards. No? I see one. It's a hard one. It's not one that you guys made.
What's a proportional relationship?
Well, and how?
Okay, on my wall of functions,
Yeah.
why would that linear be proportional? Yeah,
It starts at the origin and goes in a straight line.
it starts at the origin. Okay, it goes in a straight line. Does anybody know what the unit rate of that one would be? Probably someone in that far group over there could see.
I know, I don't see it.
Will?
1 to 1.
Yeah, the unit rate's 1 to 1. It goes rise over run, up 1 over 1. So that's our unit rate. Okay, we saw a linear relationship. We talked about why that was linear, and we saw a nonlinear relationship, and we talked about why that was nonlinear. Okay, so today's focus is mainly linear, and we're gonna, I'm gonna give you the situation, and it's kind of a fun one. Oh, I put up some other pictures when we did the proportional. Wait, which one of these three was proportional? From our labs when we did proportional relationships? The second one? Do you remember what the relationship was, what station this was at?
The pendulum.
Okay, so William says it was a pendulum. How many times does a pendulum swing? Over a certain amount of
I
time.
don't get how it's proportional.
I know it does. It seems like it would because it slows down. It's not going the same distance.
Yeah, later on, it doesn't.
Okay, so yeah, it's kind of a tricky one. I agree. When I first heard this, I'm like, no way. And I pulled out a pendulum and I started swinging it and I started timing it and I'm like, wow, it really is proportional. Because the first swings are like really big, right? And then they
they're
get
really fast.
smaller.
And like when they get smaller, it gets lower, and then yeah.
Yeah, so you wouldn't think
It
that,
loses speed.
but it does. It's proportional. We showed it there. So here's our challenge for today. Okay. One of the annual events at the school during Spirit Week is a tricycle race held in the gym. That would be fun for our team assembly, right?
Miss Leslie rode
Yeah.
a tricycle race.
Okay, it's not Miss Leslie, it's Leslie. Okay, Leslie, a member of your class, has won the race each of the last 3 years and is starting to brag about it. Okay, the rest of the class is annoyed by this attitude and wants to end the winning streak.
This ending.
Okay, win this winning streak. Okay, so here is some information I'm going to give you. Okay, I'm going to tell you that Leslie rides at a constant rate of 2 meters per second. Okay, Dina wants to see if she can win the big race with a 3 meter head start, and she can ride her tricycle 1 meter per second. Dean estimates he can ride 3 meters every 4 seconds and wants a 2 meter head start. Bob usually rides 3 meters in 2 seconds and will get a 5 meter head start. And then last, we have Elizabeth. Oh wait, we have Brian too. Elizabeth rides 1 meter in 4 seconds and wants a 6 meter head start.
Sure.
And last, Gabriel, I'm gonna have you think through this for a minute first, okay? Brian starts 3 seconds late and catches up to Dina 7 seconds after the race begins. So you have a lot of people in this race.
What?
I'm going to give you guys just 2 minutes in your groups to talk about how could you decide who won the race and if you have all the information you need to see who won the race.
Wait, how long is that?
We do have the information.
Well, like, we know that Leslie's riding a constant rate of 2 meters per second.
Yeah.
That you should say.
And then,
So how long is the race?
I don't know. It never says how long the race is. So
yeah, it does say
But we have to know the stopping point.
Yeah, so that's why
I know,
I don't think we have
exactly.
enough information.
what are we trying to figure out though? Are we trying to figure out
It seems like
how fast
everybody has
Brian goes, or
How if anyone can beat
2
Leslie?
meters per second, so that would be 4 meters in 2 seconds.
6 meters and 3.
So,
That's what
yeah, 6
proportional
meters per-
relationship.
And then in 1.5 it would be
1.5?
3 meters. So 3
Wait,
meters is
wait.
1.5 seconds, right? Haley?
wait, for which
3
one?
meters is 1.5.
Yeah, because
For the 3 meters every 4 seconds.
Yeah, 1.5. Yeah.
No, it's not.
3 seconds. 3 seconds.
It's not. No, it's not. It's not. It's 7.75 because it's
For 1 second.
Plus 2
Or 1
meters.
meter.
for
So
1
2.75.
second. It's 0.75 meters per second.
Oh, we have a paper.
That's what Dean goes.
Well, it would be 2 meters per second for Leslie though.
For Leslie.
It would be 2 meters per second. So then for 3 seconds, it
You
would
guys,
be.
I'm gonna have you come back and I'm gonna give you some tools to help you solve this problem.
Suppose the finish line is 25 meters.
I will get those for you in a minute. Okay, so Matthew's group and Gabriel and William. Haley. All right. Haley, you're William. Okay. So let's really quick talk, and then I'm going to give you some more directions because this was really a hard question. This group over here was talking about what's something that you think you're missing. Hey, Alex.
How far are the races?
How long is that race? Because do we even know how long the race is? What did you say?
It could be anywhere for it could be 2 meters long and it's over in a second, or it could be like 20 meters long and and you would never know exactly who's gonna win because someone could be in the lead, but it doesn't matter because the distance.
Yeah, so this whole problem and who's the winner really kind of does depend on how long is the race. If it was 2 meters long and he gets a 5 meter head start, he's starting 3 meters past the finish line. So that's kind of silly. But if it was 20 meters long, does that give him enough of an advantage? I heard some really cool stuff from this group over here. So what were some thoughts that you had about each of the rates?
We were looking to see how much it would be per second for each person, but we couldn't figure out who would win again if we didn't have the ending distance. So
Okay, so I liked what Haley's group was saying. They were saying, well, Dina goes 1 meter, but you get to add 3 meters, 1 meter per second, but you get to add 3 meters onto her amount that she's gone because she's getting a head start. So how would that look on a graph if you were to graph this with a 3 meter head start? That's something you guys are going to have to ask each other when you're working on this problem. Okay, so here is what I'd like you to do. All the data I gave you with who rides at different rates is right here. I want you to try number 1, 2, 3, and 4. And I'm going to give you guys about 10 minutes, and then we'll stop and see where you're at, and then another 5-10 minutes, okay? And please work in groups and figure out how to do these problems together, because singly it's going to be a little tricky.
I should graph it. 3 meters in 2 seconds.
And see who finishes the race.
5 seconds. I can do the 5 myself.
Do you know how to do it? Can use some color pencils. 2 meters.
You should have your own colored pencils, but just in case you don't.
I have my own.
We have some too.
Just bright colors. I call red and orange. Yeah. That's a really pretty color too.
Okay, so where would everyone be at 12 seconds?
Yeah, she cries so much she doesn't need a head start.
Yeah.
So no.
So that's, and then second,
She would finish the race in
we're
12 and a
assuming
half
that these
seconds.
are like robotic people that are tired.
Yes, they ride at a constant rate, so that means they don't slow down and they don't get tired. Yeah, you should have your own colored pencils, but just in case there's some for you.
I'm using my own random ledger stuff. Okay, but so if Leslie would ride at 2 meters, it would take her how long?
Bob wins.
What is it?
By
11.
point.
Yeah, because it's 11.
Oh no, by like point what's it, 7
You guys,
or like
if you need
0.8 seconds.
rulers,
Bob
you
wins.
know where to find them?
This is her time.
22.
Bob's time.
Yes.
But Bob's time would be
I
longer
don't think it
then.
matters. I right.
Because 12 seconds.
Maybe it says in the
Oh, wait. Leslie would win.
Never mind.
And it says it right in the top of your description too.
Wait.
Okay. So, yeah.
Wait,
so
he
Leslie
starts at 20, right? So that's 20 meters. 3 doesn't go into 20. 3 goes into 18. Can you divide 3 into 20?
Leslie,
No.
20 divided by 3.
Yeah.
That's 1.33.
So Brian has around 1.8. You find that out exactly. Around 1.8.
And then Elizabeth is writing at. That's pretty sad.
That's his sister.
He's going. Elizabeth is going at 4.25.
So are you figuring out how long it takes each of them to take the?
Yeah.
Okay.
You already know that Dina would not beat Leslie in a race.
She needs like a 20-meter head start.
Pretty much. She would get there in 5 seconds. That's a long time.
It's lost by 0.8 seconds.
Oh, now,
Can I
okay.
give your group graph paper?
And Bob
You're just trying it a different way. So I
Bob
see
went the fastest.
Jacob here is figuring out how many meters per second they go.
How long it would take them to finish them,
Okay,
especially with
with the head starts. Okay.
So,
And
but
Haley's making a graph.
Oh, we need 5s.
so then Bob would go 1 meter in 1.5 seconds.
Bob would go what? 1 meter and
1
1.5?
meter. Or no. 1.5 meters in 1 second. Yeah, that's what I meant.
Dean would be at 11 meters, but if you have to subtract 2 meters, like so, like you say,
you're adding. They're head starts. They're not disadvantages. They're advantages.
oh, she's at 11 meters.
Yeah, it's a head start.
No, she's at 14.
So when they start,
No, but look,
instead of Dina being like,
No, don't start them at that number. Start them at where we were starting with all of them.
Alex, I want you to share your graph with these guys just to kind of explain what are you doing on the side here.
wait, is Leslie at
Okay,
24?
just explain that and then see if that makes sense to them or if they have something that would make it different.
so
Okay?
like the meter head starts, like the 2 meter head start, you just put it at 2 meters
And
already.
you guys are just figuring out how long it's going to take each to go 25.
So far, nobody's beating Leslie, but somebody has gotten close.
Not 25 meters,
E, right, Bob?
Yeah.
Okay.
not 25 meters, but we're doing like, we're including their head starts.
Okay.
So we're subtracting their head starts from the 25 meters. And then,
Got it. Okay.
yeah.
That's perfect.
Okay. Now, how long would it take Elizabeth? 1 meter in 4 seconds. That's not very fast.
That's really bad.
I'm guessing she's gonna
So you
lose.
guys, this group I see a lot of people attacking in different ways. Brian, Hannah, can you tell John and Alan what you guys are doing?
How much they have to go for the race, so minus their head starts, and then how many meters they can go for every second.
Okay, so they're figuring the meters per second and then subtracting the head start. And then Alan and John, how are you guys attacking?
We're just putting in the head starts and just see how long each distance is, and whoever has the shortest graph, like the straighter graph wins.
Okay, so how are you putting in the head starts into your graph?
Just putting in 3.
Okay. Okay, so you're putting in 3 like right there?
Yeah.
Okay.
So basically, let's just find out what it's going
Okay. So you guys are attacking it numerically, you guys are attacking it graphically.
How do you figure out Brian?
Which one?
Brian
Brian.
starts the second minute.
3,
I'm gonna let you struggle with that for a minute.
5. Okay, he starts with a 5.
Think about what would his rate have to be to catch up? Okay.
5. Normally that's 2 seconds.
So then how far would she would get?
We figured out how fast they go in a second.
Okay, and we
How
call
far?
it the unit rate, so you figured out that, well, that unit rate or slope for each of these.
And then
So now what's your next plan? That's a good start.
to find how long it took everyone to finish the race.
Okay.
Well,
If someone gets a 3-meter head start, how are you going to adjust their race?
Just get rid of those 3 meters, because they only have to cover the smaller distance, or cover the distance in front of them.
Andrew.
Like,
Okay.
No, wait, hold on, wait. Bob doesn't ride at 1.25.
he runs at 1.5.
Yeah, 1.5. But Andrew.
Oh my God, Andrew.
But Andrew.
Brian starts. Okay, I'll
Yeah,
find
because
Brian.
Leslie.
I divided right.
No, but hey, Andrew, Leslie finishes because she in. Andrew.
16 at 16, 20 at what? 20. Okay, yeah, he's lost. He's by far. Okay.
So I'm gonna come back to you guys because I like what you guys started with, just the numbers, figuring out what their rate is, and then you started with making a graph. What are you thinking you like? Do you like the graph or the figuring out
I like
the
the
numbers?
graph better. I think the graph is
It
way
kind of
easier.
just shows you who's going where.
I wish we would have done the graph first.
Well, no, both ways are useful.
Yeah, but I just think it's easier to do the graph because
Okay.
you can see it more clearly, I think. Like,
Yeah. Okay, so Bob, I think, he starts 5 seconds at 5 meters at 0.
guys, we know that Leslie won with a time of 12.
Yeah, but I still need to graph it anyway, so we
3
might as well
meters in
graph
2
it just to make
seconds.
sure, you know?
Wow, 3 meters in 2 seconds. I'm
If you
impressed.
wanted to put the information onto a graph.
11.
Bob to win now.
He's winning right now. 4, 6. Oh wait,
No.
3 meters.
Dean goes. How far does Dean go?
Dean is. He has a 2-meter head start to accommodate for that.
So 20. He's.
23. What?
Oh no. Dinah has a
I
22
know you keep
second.
finishing this way with Brian, but then I want you to go back and try
Dean
the
goes,
graphing way and
so
see if you
20
can see which way you prefer and which way's.
So we just have to. I really want to calculate it.
Distance from the starting line, is that like their, where they
Yeah,
start?
so-
Dina, right, finish that starting or no, Leslie and Brian.
Leslie and Brian, yes. It would be a 0
Well,
on
even
the
still though, this is all going down and hers is going up like this, so I think Leslie wins no matter what.
Yeah, Leslie wins. He ends right here.
Okay.
So Bob, but I don't know. There could be somebody that's faster. I just don't know.
Okay, well then let's just keep going.
Did you guys figure out how much it took them for each person?
How are you doing, Gabriel?
Okay, Elizabeth.
That took really well.
Okay, so let's try this out. Okay. Leslie rides at a constant rate of 2 meters per second. Okay, this is a distance from the starting line, and this is 0 time. That's where you're starting. So where is Leslie going to start? At -3?
She's going to. No. This is Leslie.
Okay, so what you're telling me right now is Leslie starting, this is time. Leslie is starting 2 seconds late. Does Leslie start at 2 seconds?
Leslie does 2 seconds.
Okay. How about we start Leslie at 0, 0, and I'm going to work you through Leslie, and then we'll kind of work on going through Dina. Because she's gone,
Does Bob win?
let's think about this. In 0 seconds, how far is Leslie
Did
gone?
Bob win on yours?
Yeah. Okay.
I think
Now,
Brian
let's
tied
go
with
over here to 1 second.
my graph,
In
it
1
seems like
second,
Brian
how far is
tied.
Leslie gone?
With
Yeah, so we're going to put a dot right there for Leslie.
my graph, Brian tied.
No. This
Wait, where's
is
your
1
Brian?
second right here.
Where's your Brian graph?
Okay.
So wait, each of the persons.
Brian is just, you just want to, it's 7 meters.
getting
You
it
pull
now?
back 4 meters. You
So
pull back
there's
3
Leslie,
meters.
and then you go 1 second, and she's gone 2 meters.
This delay, so that means you pull back
And then
3
you go 1
meters.
more second, and she's gone up 2 more meters.
Yeah, so she does. So she's at a constant.
Does Bob win? Because he seems like he won.
Okay, you have to prove to me that he won.
Okay.
And you've got Hannah and Ryan and John here helping. Okay, so you've got Leslie done.
Did Brian win? I mean Bob.
Okay, how would you put Dina on there?
Okay, Ryan,
She's starting at a
Ryan, did
3
Bob
meter
win on
head
yours?
start. So where would Dina start?
Oh. Bob is the second one.
Awesome. And then she goes 1 meter per second. So after 1 second, where is she going to be at? How many
Cheese
meters?
mania.
So wait, she can ride a train about 1 meter per second. So that is super duper slow.
What's a constant of 6, 6, 6, 6, 6.
Awesome.
6, 6, 6, 6, 6, 6.
Miss Sarah, can we use a calculator?
Yes. Okay. You guys, 2 minutes and we're going to stop and talk about this. You don't have to be done. But 2 minutes. Okay?
I messed up. Hey, do you have, what's your white eraser?
Am I doing this right?
What do you think? So this is Leslie. Okay. Oh, there you are. Okay. So Leslie went in 1 second 2 meters, another second 2 meters. It's pretty good. I would be a little bit more precise on your graph.
Okay.
Because or Haley, can I borrow your graph for just a second? Okay.
Or I could make dots like every
Yeah, she did dots, but like you said, I would probably do the dots and then connect it. So, because there's a lot of dots in here, but you can see who's here. Thank you. You guys came up with who?
Yeah. So 1.5. 25.
Okay, so now I see that you guys did it all like with calculations. How would you draw the graphs?
Oh,
I want you.
we did a scatter plot.
We did a scatter plot
With 12 seconds. 12 seconds each.
Okay. Oh, so at 12 seconds, where are they at?
Yeah.
Okay, I want you to make a linear graph. So where would they be at 0 seconds? Where would each of them be at?
Well, they. Oh,
That's easy.
yeah, you count the head starts.
Yeah, you just
Okay, so where would Leslie be?
Leslie's G would be at 0.
Okay, so Leslie would be at 0.
Start. It does not
Sorry.
have a start.
Leslie.
Okay.
Arguing whether it's a girl or a boy, so we have to call it it.
It doesn't have. So after 1 second, where is Leslie at now?
After 1 second, she is
Leslie
She's at 2.
is at
Uh-huh.
2.
And then after another second, where is she
Okay,
at?
so you want us to do like just a linear.
Okay, so this is saying after 2 seconds she hasn't gone anywhere. She's after 1 second she's gone 2. Yeah, so you'd be at 1, 2. Yeah. What do you think you would do if you connected Leslie's starting point with where she ended up at for the 25 meters? What do you think about these
Elizabeth is really depressing, and she got a 3 meter head start.
I'm gonna go grab a graph and kind of show you.
Oh, we know what you mean.
I'm gonna borrow your graph really quick, okay?
Oh,
And I'm gonna give it right back to you.
oh, guess who's
So here's what John did with his graph. I want you to think about it. I was right. Why do you think this graph would be a little more useful than just having the ending times?
Because then all you know is where the person was at a certain given time, and you don't know their unit rate per se.
Okay.
I guess you could find that based on that information. But
Okay. This just gives me one piece of information. Where are they at 12 seconds? Whereas this one I can say, where are they all at 5 seconds? Where are they all at 10 seconds? Okay.
I can't erase mine, so I have to get a new one.
Thank you, John. Okay, you guys, 2 minutes is up. We're gonna stop for just a second. We're gonna talk about what you've done. Okay, how many people just started pulling out like their arithmetic and started dividing and figuring out what the rate was that each person went per second, and then added on head starts? In this group, how many people started that way? Okay, Hagen, Jacob, in this group back here. I think the whole group did. You guys we're gonna get this figured out using unit rates and arithmetics. Okay, what about this group right here? Did anybody start right away with doing calculations versus the graph?
Yeah.
Well, we kind of used the graph.
We used the graph with the calculator.
But
Okay, so they did a little bit of calculation, but then showed that on the graph.
We used the number 12.
Okay.
Because it was divisible by all of their seconds.
Oh, okay, so did you hear what Parker said she did? every rate that they had could easily be fixed or be used with 12 seconds.
Yeah.
Okay, so all the unit rates would end up at a certain place at 12. So they did 12 seconds as a baseline to see where everybody was at 12 seconds. Okay, over here, John and Alan, you guys jumped right into the graphs, and Gabriel kind of jumped into the graphs. Hannah and Ryan, you guys did the calculations. Okay, what did you guys think about the calculations? How are they useful in solving the problem? Let me say that. Is that a little better question? How are the calculations useful in solving this problem?
They can tell you how fast each of them go
Okay, they can tell you how fast each is going.
and how long it takes them to go 25.
Okay, and then using those, they can figure out how fast it takes to go 25. Okay, Alan and John did graphs. So Alan and John, are you guys, John?
Yeah.
Okay, why do you think using the graph was helpful for you in solving this problem?
Because you don't have to do any of that mathy stuff. You just have to put in the dots on the graph, and then you kind of know who finished first by whoever the graph is straighter, and then whoever reached 25 first.
And I'm kind of the person who likes to do the calculations, but I know this is a really bad reason, but I just did the graph first because it's what I got first.
Okay, so you got the graph paper first, so you started with the graph. And Alan said it's easy to see with the graph. You still have to do some calculations with the graph.
Yeah, but I after did that after calculations, I noticed that some of my graph is off, so that's why I figured it out.
Okay. Go ahead.
Yeah.
Sorry.
So in the graph, also it's like you'll get kind of off because the numbers on the graph is sort of off. Like the 5, 10, and 15, and 25, and so on and so forth is kind of off. So that makes it off. So it's kind of hard to decide what's the actual pattern.
Okay. I'm going to come back to that in a second. But I'm going to kind of summarize what I think I heard Alan say. Is after he did a couple calculations and plotted those first couple points on the graph, he could just continue the line and not have to keep repeating the calculations. Is that what you were saying?
No, like the actual numbers on the graph is sort of off, like this 5 and this 10 and that kind of stuff, and that kind of ruins the graph numbers.
Oh, okay. So he thinks the 5, the 10, the 15, the 20. Oh, okay. It's not evenly on the space.
Yeah, so
the line.
Yeah, so that's I sort of used that, and it kind of messed up the graph.
Okay. So don't actually count the lines. We'll have to fix that scale. Sorry about that. I see what you're saying now. All right, this group over here, you guys really stuck with the calculations, and then I kind of pushed you towards the graph, right?
No.
No, I never pushed you towards the graph? Okay, just calculations. What do you guys think about your calculations, that method?
What's 2 meter and start at 6?
Yeah. You don't know? Okay, all right, so there are multiple ways to solve this problem. Did anybody figure out who won the race at 25 meters? Chloe.
We knew it was Leslie because when we calculated, we didn't really do the, what we sort of did. We started off with the unit rate, and then we just figured out how long it would take them to get to 25 meters, and then calculated their head starts and everything in there. And Brian's starting 3 seconds late. And Leslie won the race with 12.5 seconds as her time from 0 to 25 meters, which was the least amount out of the
Okay, so Leslie got first. Did anybody figure out who got second? Well, this group probably did. Alex, but who did you guys get for second?
Bob.
Who?
Yeah.
Bob. And how many seconds did it take Bob?
20. For which race?
For the 25 meter race. Alan.
13.33333.
13.3 repeating?
Exactly.
Okay. Who came in third place?
Someone.
Dean.
Haley.
Brian.
Brian. And how many seconds did it take Brian?
Oh, that's because that wasn't
14.5. Okay, I'm going to pull up a graph, and just to show you guys what the graph would look like, and we're going to go here.
15 different ones. 3 meters every first. Hey, write this down. Oh, 3 didn't. 3 meters.
Okay, so here's my graph. Chloe.
say, but with Brian, don't you have to add on to the 14.25 the 3 seconds that he wasn't moving at all?
Okay, so Haley, when you figured out 14.5, you guys were the ones that said 14.5, right? Okay, did you add that 3 seconds that he was?
Well, I made a graph originally, so I started him at 0 meters at 3 seconds.
Okay, so right here?
Yeah.
Okay, so here we have Brian. Okay, how can I use this graph to figure out who won a 25-meter race? Logan, do you want to come up and show?
I'm assuming I got it right, but
Well, let's just talk about how we could look at this graph and figure it out.
you just kind of like stop the graph at 25.
Okay, here, I'll let you do that.
Like that.
Okay, so we're going to stop this graph. I'm going to make it go down here to 25. How could you use that to decide who won the race? Jacob.
Well, it kind of, if you put it on a graph, the larger the slope there is, that's how fast they're going.
So the greater rate means they're going, or the greater slope is a greater rate or faster rate. Okay, so we're looking at this line at 25 meters. Anybody want to talk about how I could use this line at 25 meters to decide? Donovan.
Whoever has the farthest to the left is the winner at the 25.
Right here. Why would this one be the winner?
Because it's the closest to 0.
Yeah, if you go down to the seconds, they went the fastest. Okay? And then after that, we have Brian, Bob, Dina, Dean. Elizabeth's never going to make it. Just give up. No, never mind. Never give up. Persevere. How would the race change if I had 35 meters? Would it be the same? And how could I use this graph instead of doing the brute force like you guys did with some of the calculations? Chloe. You can go, Logan. Thank you.
When you continue the graph, we're going more learning to line straight, and then stop it at 35. Brian has a faster time to reach 35.
Okay, so looking at this graph, if we decided to make our race go 35 meters, who would win? Brian.
At 25.
At 25, it's really close.
But it's still
If Brian wasn't stupid and
Brian's right, never
This graph
mind.
is off. This graph is off. Because instead, you should move it this way. Like put the starting point right there, and then that would make it different.
But Brian started 3 seconds late.
Oh yeah, huh?
Yeah. Okay.
if he wasn't an idiot and
all right.
started at 0, he would have won.
So today we looked at linear relationships and rates and patterns, but we took it to a real world side instead of just the tile patterns like we did the last time. What do you think about this?
What's that?
It's good? Do you like it?
It tastes.
Okay, I'm going to give you guys a check for understanding to see how well you guys understand this. And in the check for understanding, well, first off, why don't I talk about what your homework is, and then you'll have 5 minutes to do the check for understanding. You're going to do side 2 of the big race. It's kind of extending what we did in the class. Do you remember slope? I heard Jacob use the word slope. That was good. What is slope?
It's the
Will. Sorry.
Rise over run, so change in y over change in x.
Change in y over change in x. Okay. Logan, do you have another name?
Rate of change.
Rate of change. Will, do you have another? Will, do you have another name?
Rise over run.
Rise over run. Change in y over change in x. Slope. Okay. So
Unit rate.
unit rate.
Yeah.
When we're looking at proportions, it's at unit rate. Okay. This got turned off. Y-intercept. That might be a new word. Does anybody want to take a guess at what you think a y-intercept is? Jacob.
It's on a graph when whatever line you have, it intercepts the y-axis.
Okay, so let's look at that graph. What would be the y-intercept of Elizabeth?
That looks like
6.
yeah, or 7.
6.
Oh yeah, 6.
Okay, the y-intercept is where it intercepts the y-axis. Okay. All right, I'm going to hand out a little half sheet for a check for understanding. The first question is, if you came in 4th place in this race, what could one of your rates be? Okay, so if you came in 4th place, what could a rate be that would have made you come in 4th place instead of 1st, 2nd, or 3rd? And then the second question, you guys will just rate yourselves. And thought I had these out, but I don't. So what I'd like you to do, you have about 5 minutes. So answer these, check for understandings. Yeah. AMC 10, people who took the AMC 10, you'll find out results around the end of February.
Oh, it's so long to wait. I feel sorry for you all. Because I didn't do it. And it's a long time to wait.
Okay, so again, your questions are, you jumped into the race at the last minute, you came in 4th place for the 25-meter race. What rate could yours have been? Justify your answer, and then name at least 2 different ways you can represent linear relationships and why. Sorry, Chloe and Logan.
Place, seriously? That means if I jumped in, that means if I jumped in right on the start of the race, I could like.
And if you didn't have a head start?
I'll let, if you want to add a head start into yours, you can. But I'm going to say you don't have to have a head start. I wouldn't have a head start. No, because then you'd win. You want to come in 4th place.
Unless you were like slower than Elizabeth.
Unless you moved in negative time.
At the last minute, if you went backwards,
Okay, at the last second, that was just an expression. Like, wait, I want to race too. And you run and jump into the race as soon as they shoot the gun to start.
Oh.
Yes.
Like that guy on left one thinking, what if like someone jumped in the race and at the last few nanoseconds an interstellar spacecraft came roaring in there and took 4th place?
Okay, you could do that. You could say I'm an intergalactic stellar spaceship. And I go at a rate, I got a 24-second head start, and my rate is this. Or you could say a 24.9 second head start. That's fine. If you want to be creative, perfect. What are you guys thinking? Are you stuck? Not really? Why do you have to get 6th place? Okay. You guys, when I say jumped in at the last minute, that means it's an expression. Right when they were about to start the race, you jumped in and did the race with everyone else.
Said at the last second.
What if you like work those tricycle races and just do that?
Okay, so I would look at like, what are some rates that these guys are going? 14.5 seconds per 4 meter or per 25 meters. So could you come up with a rate that would put you somewhere between 3rd and 4th place?
You could. Graphs and tables.
20 seconds.
Yeah.
Okay, how are you guys doing?
What does it mean, like, at the last minute?
That just means right when the race is about to start, you jump in and do the race with everyone else.
With a 3 second. It could be a 3 second stuff.
but Bob went
And then graphs.
Okay, you're fine.
Graphs and tables. It represents.
Okay, who would like to tell Ryan what a y-intercept is?
I don't know myself.
We just talked about it. Jacob told us what a y-intercept was. Think about in a graph. Where do you think a y-intercept on a graph would be?
The y-axis.
Yeah, so let me pull up this picture. Okay. Here's Elizabeth. Where's Elizabeth's y-intercept? And so what's that number? 6. So Elizabeth's y-intercept is 6. Whose y-intercept is 3? I know, I can't see either. I'll pull that down. Whose y-intercept is 3? Dina's. Okay, so that's what a y-intercept is. Okay, you guys, we have about 2 minutes left. Okay, I want you to answer these questions as best you can. Okay, and When you're done, you're gonna leave your check for understandings in the middle of the desk and I'll collect those. We're kind of in a different format today, so I don't have the row folders out. So just leave them in the middle of the desk and I'll collect those all. Okay? Hagen, how are you doing? Did you fill this part out? Did anybody in your group fill that part out? This could help you. Okay, write your name on it, leave it in the middle, blank. Yeah, what would be your rate? Okay, what I want you to do is fill out the best you can, leave it in the middle, finish this up for homework, and then when you come back tomorrow and I hand it to you, I want you to think about that question again, okay? Yeah. All right, I'm gonna finish up. All right, so again, check for understandings in the middle of the desk. Ellen, what did I just say?
Yeah.
What did I just say?
Didn't hear you.
I know. Check for understandings in the middle of the desks. Okay. Second side of the homework, or second side of the big race is your homework. And again, we're trying to see that connection between linear relationships and these patterns that we looked at yesterday with now real world situations. Chloe. Yes, finish the first side if you didn't get the first side all the way done. If you didn't get the check for understanding done, turn it in. I want to see how you did, and then we'll talk about it at the beginning of next class, and you might have some more time then.